Gary Maxson is one of our membrane specialists at Caloris. He's a leading expert on membrane cross-flow separation technologies, including microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. He has 30 years experience designing membrane systems utilizing spiral, hollow fiber, ceramic, and stainless membranes for sanitary and industrial applications. So without further ado, I'm going to turn it over to Gary.
Well, thank you, Missy. Good afternoon, everybody. Again, my name is Gary Maxson. I'm the Filtration Engineering Manager at Caloris, and today our presentation is going to be on RO filtration for boiler feed water. Okay, so this is a typical boiler process flow diagram. The variables we're interested in are the type of equipment being used to reduce the dissolved solids going to the makeup water for the boiler. Typically you'd have a water softener, maybe an RO, maybe a mixed bed DI, a portable exchange DI, or even an EDI. And I'm probably missing a few. And what this equipment is going to do is going to reduce the total dissolved solids. You're going to have a certain alkalinity, a certain silica, a certain hardness, among other minerals. So here are the equipment. You're going to have the boiler water makeup tank, and then you'll have a feed pump, pump it through the deaerator. You'll probably have some pH and chemical addition before that deaerator. What we're worried about on the boiler is the feed water and blow down, and most importantly is what kind of cycles that boiler is doing. Cycles is just going to be the feed water divided by the blow down. And you can see there's some various formulas I have shown here to get that. So a little bit about what kind of equipment you can use for boiler feed water. The simplest process is probably a softener. Softener is an exchange method of treating hard water using zeolite resin. To remove the hardness ions, the zeolite resin just exchanges the hardness ions with sodium ions. And then the softener is regenerated by back flushing with a salt brine solution, which exchanges the hardness ions with sodium ions. Okay, some disadvantages of the water softener. There is no reduction in total dissolved solids. There's no silica, chloride, or alkalinity reduction. And it's usually limited to low pressure boiler operation. The effluent quality usually limits the boiler cycles, and it's going to have high chloride discharge and high salt usage. The advantages are it's very inexpensive to run, it's simple, durable, and it's safe. A more complex process is the mixed bed DI. This is an ion exchange method of treating water with cation and anion resins. To remove the water ion impurities, cation and anion resins exchange the ions with hydrogen and hydroxyl ions. The cation and anion resins are regenerated by backflushing the anion resin with a strong caustic and the cation resin with a strong acid. This exchanges the ion impurities with the hydroxyl and hydrogen ions. And I can tell you the regeneration is a lot more complicated than what I just said there. Disadvantages for a mixed bed DI, you're using hazardous chemicals for the regeneration. You have high and variable chemical costs. The anion resin life is limited. It's manpower intensive, and high TDS usually corresponds to high operating costs. The advantages are you're going to have excellent reduction of all dissolved solids. It's going to be suitable for high pressure boilers and even steam turbine generators, and it can achieve high purity water. Another simple process is just renting portable exchange DI tanks. This is similar to a mixed bed DI. It's an ion exchange method of treating water with a bed of cation and anion resins, but will usually include 2 or more mixed bed tanks in series. You'll have a primary and a polishing. Once the tanks are spent, they are shipped off-site to a service center, and thereby avoiding the issues with on-site chemicals. Disadvantages: high and variable costs, limited service centers. Again, high TDS equals high operating costs. The advantages, same as the mixed bed DI, but no chemicals. Okay, so what this presentation will mainly discuss is reverse osmosis. Reverse osmosis is a purification process that involves pressure and a permeable membrane to separate ions and particulates from a water stream. The driving force for the process is the pressure over and above the osmotic pressure of the feed solution. Generally, higher TDS in the feed water translates to a higher osmotic pressure. That's why on a seawater RO, you're probably going to run pressures of 1,000 PSI, whereas in a brackish water, where you have TDS of, 800 to 1,000 or around that area, you're going to only be running pressures of 250 PSI or less. For an RO, to prevent fouling, usually you're going to use an anti-scalant, and high membrane cross-flow velocities are required. Now the RO will generate a purified permeate stream and a concentrate stream. Okay, so for the reverse osmosis, disadvantages: not suitable for high pressure boilers greater than 1,000 PSI alone. You might use it in combination with a DI system, but alone it's not going to give you the water quality needed. It's going to have high electrical costs, a significant reject stream. It does not reject carbon dioxide. It's susceptible to biofouling, and it requires pre-treated water. So if you have free chlorine in your water, you're going to have to remove that, and suspended solids are going to have to remove too. You definitely don't want to have a lot of suspended solids. The advantages: all the solids are rejected. Long periods between cleaning. Operating costs not as affected by TDS. Enables high cycle boiler operation. Does not require strong acids or bases. Not labor intensive. And there are advantages to operating in front of a resin-based system. It will definitely reduce the operating costs of a resin-based system if you have an RO in front of it. Okay, so this next slide is going to cover what goes into the design of an RO. Process engineers will typically use modeling software to determine maximum recovery and permeate flows based on the feed water mineral analysis. So for an RO, the main equipment are going to be, for pre-treatment, you're going to have to have your chemical pumps. It might be antioxidant. If you got chlorine in the water, you might, you're most likely to have an anti-scalant pump. And if you want to get really good recovery, you'll probably want an acid pump too. And you always want a pre-filter in front of the RO. The main piece of equipment is going to be that feed pump in front of the RO, and then, of course, the RO itself. On the process side, for this example, let's just say we got a boiler that requires 80 GPM. So from that software, we determined already that we can, by using anti-scalant and acid, we can get to an 80% recovery on this particular RO. So using that, we could use that recovery formula to end up getting a feed of 100 GPM based on an 80 GPM permeate rate. The concentrate going down the drain is going to be the feed minus permeate. That'll be 20 GPM. One other process thing, a rule of thumb, if you want to know how clean your water is going to be on the RO, you can use the formula of permeate TDS is going to equal to 1 minus the reject times the feed sounds. So our rejection for this RO membrane is 99.5%. That's probably typical. I've seen membranes a little bit higher, a little bit lower. So anyway, if we take that 800 ppm of the feed and multiply it times 1 minus 0.995, we should end up with a permeate of about 4 TDS. Okay, so a little bit more complicated RO design is the double pass RO, and the beauty about this one is it's going to remove CO2. So what's going on here is you have a regular RO. You're taking the permeate from the first RO, which has CO2 in it. That's actually your main impurity, is that CO2. And you're going to run that stream into a second RO, and before you run it into the second RO, you're going to increase the pH to 8.5 using sodium hydroxide or potassium hydroxide. And what happens is that CO2 will then be converted to bicarbonate and carbonate, which can be rejected by the RO. So all that bicarbonate, carbonate get rejected. You'll run back that to the feed side of the first RO, and the second pass permeate is going to give you much better quality water with very CO2 of basically 0. It's going to have a sodium of less than 100 ppb and silica of about 10 pp. And usually this operation is for you know, a high pressure boiler, and this will be excellent feed quality in front of a DI system if you needed purified water. Okay, so potential RO membrane solutions. One solution is a RO prior to an existing water softener. What that's going to do is going to reduce the TDS, and basically the RO is going to have maybe a part per million of hardness. That hardness going to the water softener is pretty good, much going to reduce it all, so you're going to have a pretty good stream then going to your boiler. And the real beauty is that water softener, instead of having to be regenerated every 4 hours, you know, it's probably not going to have to be regenerated for you know, 1 to 2 months. You can also just use an RO to replace an existing water softener. Another membrane solution is a double pass RO prior to an existing mixed bed DI. And as I think I already said, the operating costs of that mixed bed DI are going to go way down now. So instead of having to regenerate that mixed bed DI every day, you probably don't have to regenerate that for a couple months. Same principle in RO in front of a portable exchange tank to greatly reduce the operating costs of those portable exchange tanks. And then another solution, if you want to replace your resin-based system altogether, you just want to get rid of the chemicals, is use a double pass RO followed by electro deionizer or an EDI system. And then the last, there's many potential solutions, but if you had a boiler system with an abandoned blowdown heat recovery, when we do an ROI on the RO, you'll find that the heat recovery is going to be your biggest savings. So if you abandon that heat recovery system, then RO becomes very economical. Okay, when is an RO feasible? If you have high TDS water, if handling of strong acids and caustic chemicals is a concern, if you have high chemical costs, if you have a good, or you can economically discharge that RO reject water, or you got another use for it. If high chlorides in the wastewater is a concern, or if high chlorides in your boiler feed water is a concern. You get above 200 ppm and then you got corrosion concerns, so something to look out for. Okay, so this is probably something every boiler operator is familiar with. This is just the ASME boiler guidelines for feed water in front of a boiler. What I pretty much always find is that the cycles is usually determined off that conductance of your feed water. So, and you know, it's kind of all over the map of where that conductance should be. I just put in 7,000. It really has got to be discussed with your boiler manufacturer and your boiler chemical people to find out what that conductance should be. Some other things to be concerned about is silica for these low 0 to 300 pound boilers. You got a limit of 150 ppm. That hardness, you can see that the recommendation is 0.3, which an RO probably isn't going to achieve, or a softener isn't going to achieve, but the boiler chemical guys usually have some kind of antiscalant they use to overcome that hardness issue. Okay, very important. How do you determine the cycles? As I said, it's typically based on the TDS or conductivity. So let's say we have some high TDS water. The TDS is 800 ppm, and we're just using a softener. Rule of thumb of going from TDS to conductivity is just divide by 0.64. So that's what we're doing here. 800 divided by 0.64 gives us 1,250 microsiemens per centimeter in the feed water going to the boiler. So the cycles, we're going to use that. Back here we recommended for a 0 to 300 pound boiler, 7,000 for the specific conductance. You take 7,000, divide by that 1,250 in the feed water. That's going to give us cycles of 5.6. Now another example, say you have fairly high silica in your water, say it's 35 ppm. Here the cycles determination would be 150 divided by that 35, which is only 4.3. So in this case, you know, you'd have to be running cycles at 4.3 rather than at 5.6. High chloride waters is also an issue. So you got 25 ppm of chlorides in your water, and it's a softener only. Then the cycles would be 200 divided by 25, which is 8. So as I said before, to take care of hardness, chelating chemicals are can typically used to increase the cycles, but you know, they're only taking care of hardness. They're not taking care of the silica or the chlorides. So, you know, after you've looked at the stuff, really you need to discuss what you came up with your boiler chemical supplier and the boiler manufacturer. Okay, so now we're going to do a return on investment for an RO. So this is going to be an RO that's replacing a softener. For this particular example, the key input variables are the boiler feed water is now 288,000 gallons per day. The boiler cycles presently, they're running at 8 cycles. Is there a blow down heat recovery unit? No. Boiler fuel cost, $6 per 1,000 cubic feet of natural gas. Sewer costs of $2.50 per 1,000 gallons. Water costs, $1 per 1,000 gallons. We'll have a water hardness of 282. And an RO recovery, we're going to use 75%. And I should say, you know, this RO recovery makes a huge difference. For this particular example, if I went to an 80% recovery, that actually corresponds to about a $20,000 per year savings. Okay, so first thing we're going to look at is the boiler fuel cost. We're going to just say this is a 100 psi boiler. So looking at that with a 100 psi boiler, and we'll say that the makeup water temperature is 54 degrees. So the condensate temperature is 337. So the cost to heat that water up is the temperature difference of the 337 minus 54 degrees. We have a 75% boiler condensate heating efficiency, and after going through all the numbers, that figures out to $18.88 per 1,000 gallons to heat up that condensate. Condensate chemical costs are typically pretty low. I'm just going to use 20 cents per 1,000 gallons here. The boiler blowdown sewer costs $2.50. So we add that all up. The cost to put 1,000 gallons of blowdown down the drain is $21.58, which is pretty high. That's actually where most of our savings is going to be, is if we can save on the blowdown going down the drain. Water softener costs. Just for using that hardness, we get hardness of 16.5 grains per gallon. Using all the formulas, figuring a salt cost of 6 cents per pound. Salt cost and ends up being about 47 cents per 1,000 gallons. The cost to regenerate a softener is going to be only 14 cents per 1,000 gallons. And the water cost, again, is $1 per 1,000 gallons. So the Total cost to run 1,000 gallons through a softener is $1.61. Now the reverse osmosis cost. One of the big ones is going to be electrical costs. I'm using 7 cents per kilowatt hour, and I'm also going to use some sodium bisulfite as the antioxidant to remove the chlorine. That's $1 per pound. Antiscalant, figure $2.50 per pound. For this example, I'm just going to say it has 0.5 ppm of chlorine in the feed water. Antiscalant dosage is 4 ppm. So then using that pump, the pump's probably putting out 180 psi. That's going to give us an electrical cost of 27 cents per 1,000 gallons. Some other operating costs, your membrane replacements, probably going to have to replace every 3 to 5 years. That's 4 cents per 1,000 gallons. Membrane cleaning every couple of months, 2 cents per 1,000 gallons. Cartridge replacements, penny per 1,000 gallons. And now to get our chemical costs, we're going to use that recovery. The anti-scalant cost is going to be 11 cents per 1,000 gallons. Sodium bisulfite is going to be 3 cents per 1,000 gallons. And using the reject disposal cost per 1,000 gallons of $2.50, then we arrive at a water and sewer cost of $2.17 per 1,000 gallons. So add it all up, the cost to run that RO is $2.65 per 1,000 gallons. So now the summary, and we'll use those formulas we have on the left to figure out what our future feed water is going to be based on, going from boiler cycles on the softener of 8 to going to cycles on the RO of 50. So presently we're using 288,000 gallons per day of feed water. In the future, because we're doing 50 cycles, we're going to only need 257,143 gallons per day. And that's going to correspond to boiler feed water for that RO of 179 GPM. So we probably just purchase a 200 GPM RO. So using the cost of 1,000 gallons for the softener and the cost per 1,000 gallons for the RO and what the boiler blowdown is going to cost in the future and what it costs today, the present softener cost per day is $465. The present boiler blowdown fuel cost per day is $777. The future RO water cost per day is $680, and the future boiler blowdown fuel cost per day is $111. So you can see we have a significant savings on the boiler blowdown. That's $450 per day. Annualized, that's $164,417. And if I use that, and I have to purchase a 200 GPM RO, that's going to be probably a little over a year payback time for that RO. Okay, so last part of this presentation, what to look for when buying an RO system. Material construction, equipment reliability, instrumentation, CIP, energy savings, plug and play, and service are the big ones. Material construction, feed piping, typically I see a lot of people using cheap PVC. which cracks very easily if it hit by a pallet jack or operators climbing on it. I would definitely recommend using Schedule 10 for that feed piping. Permeate piping, typically PVC. Make sure they're using Schedule 80 PVC. Skid material, typically E-coat or painted steel. Pretty much everybody uses that. You know, we see a lot. You know, over 1 to 2 years, we see those type of frames already showing signs of rust. It's typically because it gets scratched very easily, and you know the field installer usually makes some modifications. He drills into the steel, and there you go, a big rust spot. Caloris typically would recommend a 304 stainless bead blasted frame, and that's actually our standard. Equipment reliability, definitely use a top of the line equipment for your feed pump. Use an efficient Grundfos or Gold's multi-stage vertical feed pump. Make sure you use all stainless steel wetted parts. I've seen some iron base plates that they typically corrode after 1 to 2 years, and then you got to replace it already. Use good cartridge filter housings. Make sure they're built with ASME design. And then Grundfos chemical pumps. They have 1,000 to 1 turn down. That's our standard. They're top of the line. You definitely don't want to go cheap on these chemical pumps. If you lose antiscalant or antioxidant, you could ruin a set of membranes within a day's time period. So definitely don't want to cheapen out on that. Instrumentation for pressure transmitters. I'm typically seeing, you know, only using the feed and concentrate. We would recommend to have feed, intermediate, and concentrate pressure transmitters for the indication of individual stage DPs. And why that's important, RO fouling issues can be best diagnosed by knowing which stage has the abnormal pressure drop. High DP in the second stage means that you got a scaling issue. If you got a high differential pressure in the first stage, that usually means that you have a suspended solids or biofouling issue. Temperature transmitters, recommended to have a transmitter prior to the membranes. I don't know how many systems I've seen where for whatever reason the temperature got out of hand during CIP, and you know they get much above 130, 140 degrees, and you toasted a set of membranes. So very important to have some kind of temperature indication there and a shut-off alarm. Flow transmitters, I see a lot of paddle wheel type out there, and you know they probably run great right at commissioning time, but they frequently blind, and you know after a year you're going to have problems with them. We recommend to use a magmeter style on the feed and concentrate. And the big advantage for those is there's no moving parts. CIP, a lot of RO systems, they don't even include a CIP. We recommend to at least include a CIP tank, a skid-mounted CIP pump, and make sure that CIP pump is sized for 40 GPM per housing that is cleaning. And then another issue of the CIP valving is typically limited. We would recommend to include valving to individually clean each RO stage. And a lot of times CIP heating is typically not included. we would recommend to include CIP heating and controls, and definitely include a temperature transmitter for membrane high pressure temperature protection. CIP is most efficient at temperatures greater than 90 degrees Fahrenheit, and you're not going to get a very good cleaning if you're just cleaning it with 60-degree Fahrenheit water. Energy savings. We would always recommend using a VFD for the feed pump. That's where you're going to get your main energy savings. See a lot of systems where they're using feed throttling valves for their feed pump control. You're throwing a lot of energy down the drain when you're doing that. Typically those throttling valves have a 100 psi pressure drop, and that's a lot of dollars. And then you also want to discuss membrane energy savings. Depending on what quality is required, you know, the membrane suppliers nowadays offer many options for energy saving membranes. Sometimes by paying a little bit more, you can run a plant at 100 psi lower and with the same quality, and you know, those type of membranes will pay for themselves probably in less than a year. Plug and play. So, you know, your RO system should arrive fully tested. You know, Caloris is, our objective is, you know, to typically have the system arrive on site, you know, after everything's plugged in, you know, you get that startup done in 1 day. So what that requires is a single 120 volt connection, a single 3-phase connection. The VFDs and MCCs should not be supplied loose. The VFD should be configured and tested before commissioning. Should have a single 80 PSIG instrument air connection. The instrumentation should be configured and tested prior to shipment. Automated valves should be configured and tested prior to shipment, and you should have a piping pressure tested prior to shipment. For service, the vendor should offer the following: commissioning services, operator training. The commitment should not end at the conclusion of the commissioning. That vendor should offer pre-treatment chemicals, cartridge filters, and membrane replacement services. You should definitely have a high level of communication for that first 2 to 3 months following commissioning, especially for inexperienced RO operators. So that's the conclusion of my presentation. If anybody has questions, you know, please submit them to Missy.
Yeah, we actually do have one question, and if anybody else would like to ask a question, please feel free to use the Q&A feature. The question we have is, what are the common antioxidants used for the chlorinated feed water?
It's usually a bisulfite, sodium metabisulfite is what's commonly used, and it's usually a 38% solution, commonly purchased.
Okay. All right, Gary, I'm going to ask that you stop your screen share there. And if anybody else has any questions, in the meantime, I'm just going to go through a couple reminders. This is part of a new webinar series we are offering on Thursdays at 3 o'clock. Next week, we will have Jim Kent doing a session on spray dryer troubleshooting. And you can register for that and any of our upcoming webinars either through the pop-up links on our homepage, or all of our webinar recordings and upcoming registration links are at this URL that I'm going to read now, caloris.com/caloris-webinars. And another way that you can keep tabs on our webinar series is by joining our mailing list. We're offering a new e-newsletter that comes out once a week to our customers on Wednesdays. And in addition to updates on things like our webinar series, we're also providing links to industry news and other resources for plant managers. I do have one other question that's come in. Is there a preference between AOX versus carbon filters for chlorinated water?
Usually it's carbon filters. I'm not, to be honest with you, I'm not even familiar with AOX, but what I've generally seen is the carbon filters.
Okay. So if anybody else has any additional questions, oh, it looks like he meant antioxidant filters. So if anybody else has any additional questions, feel free to put them in the Q&A feature. Otherwise, you can also send questions to info@caloris.com. That goes directly to me, and then I can pass those along to Gary. And we're also taking suggestions for future webinar topics that you'd like to see. In addition to next week's webinar, which is Thursday, May 7th at 3 o'clock, the following week on Thursday, May 14th, we're offering a webinar on MVR evaporator upgrades. And Jim Kent will be leading both of those sessions, the spray dryer troubleshooting and the MVR upgrade webinar over the next 2 weeks. So with that, I want to thank everybody for attending, and we hope to see you at a future webinar. I hope everybody has a great rest of your week and stays safe and healthy.
Thank you, everybody.
Thanks, Gary.